Imagine getting a distress signal from Mars and realizing the nearest rescue ship is 60 million kilometers away and will not arrive for 9 months. This is not science fiction anymore. This is the exact problem that real aerospace engineers, mission planners, and space agencies are quietly working through right now as humanity edges closer to sending permanent crews to the Red Planet. Today, we are going to walk through every single scenario in which a Mars colony could fail, and more importantly, exactly how a rescue mission would actually have to be engineered to save the astronauts stranded there. By the end of this video, you will understand why a Mars rescue is nothing like a rescue on Earth, why the laws of orbital mechanics themselves become your greatest enemy, and why the smartest minds in spaceflight consider this one of the hardest logistical puzzles ever proposed. Stick with me, because this is going to get intense. Let's start with the single fact that changes everything about a Mars rescue compared to any rescue attempt in human history. On Earth, if a base in Antarctica loses power, a plane can reach it within a day or two. If a submarine crew is trapped undersea, rescue vehicles can often reach them within hours. Even the International Space Station, orbiting just 400 kilometers above us, can be reached by a Soyuz or Dragon capsule within about 6 hours in an emergency. Mars offers no such luxury. Depending on where Earth and Mars are in their orbits around the Sun, the distance between the two planets ranges from about 55 million kilometers at closest approach to over 400 million kilometers when they are on opposite sides of the Sun. Because of this, spacecraft cannot simply launch toward Mars whenever they want. They have to wait for what is called a transfer window, a period roughly every 26 months when the alignment of Earth and Mars makes a fuel-efficient trip possible. Miss that window and you are not looking at a delay of days, you are looking at a delay of years. This single orbital mechanics constraint is the foundation of every Mars rescue scenario we are about to explore, because it means that in almost every failure situation, the crew's survival depends entirely on resources they already have on the ground, not on anything Earth can send them in time. So let's begin with the first and most immediate failure scenario, a critical loss of the habitat's life support system. A Mars habitat is essentially a life raft on a planet with a poisonous, freezing, nearly airless atmosphere. The air pressure on the Martian surface is less than 1% of Earth's. The average temperature hovers around -60 degrees Celsius, and the atmosphere is composed of 96% carbon dioxide. If a habitat experiences a major hull breach, an oxygen generation failure, or a critical carbon dioxide scrubber malfunction, the crew could have anywhere from minutes to a few hours depending on the size of the breach and the volume of the habitat. In this scenario, rescue from Earth is obviously impossible on any relevant timescale, so mission architects design habitats with redundant sealed compartments, essentially treating the base like a submarine with bulkheads that can be sealed off individually. If one module depressurizes, crew members are trained to seal it within seconds and retreat to an unaffected section while wearing pressure suits as an immediate backup layer. Every serious Mars mission architecture, including NASA's Design Reference Architecture Studies and SpaceX's Starship-based colony concepts, requires at least one fully redundant backup life support system that can operate independently of the primary system, along with buried or shielded emergency shelters, stocked with compressed oxygen tanks and manual scrubbing canisters that do not require electricity to function. The second scenario every planner has to consider is a total loss of the power system. A Mars colony's electricity almost certainly comes from either large solar arrays or a compact nuclear fission reactor, similar in concept to NASA's Kilopower project, which was specifically developed to provide reliable energy on planetary surfaces where sunlight can be blocked for weeks at a time by dust storms. If the power system fails entirely, the crew loses heating, life support, water processing, and communication almost simultaneously. This is arguably one of the most dangerous scenarios because, unlike a single system failure, it cascades into everything else at once. The engineering answer here is layered redundancy, multiple independent reactors or generators, so that no single point of failure can take down the entire colony, along with battery reserves sized to last through the worst realistic dust storm duration, which can stretch for weeks during a global dust event. Rescue planners have concluded that in a total power failure scenario, the crew's survival window is measured in hours to a few days at most, meaning any Earth-launched rescue mission is functionally irrelevant, and the entire strategy shifts toward prevention and onboard redundancy rather than external rescue. The third major failure scenario is a dust storm severe enough to block solar power generation for an extended period. Mars experiences regional dust storms regularly, and occasionally planet-encircling global storms, the most famous of which in 2018 was powerful enough to end the mission of NASA's Opportunity rover after its solar panels became coated in dust and could no longer generate power. For a crewed colony relying partly or fully on solar energy, a storm like this could be catastrophic if backup power reserves are insufficient. This is precisely why most serious mission architects, including those at NASA and SpaceX, favor nuclear power sources for permanent Mars settlements, specifically because they are immune to dust storm blackouts, a lesson learned directly from watching robotic missions struggle with this exact problem for over 2 decades. The fourth scenario, and one of the most psychologically chilling, involves a medical emergency far beyond the crew's onboard capability, such as a severe injury, acute appendicitis, a major radiation exposure event, or a serious illness requiring surgery. On the International Space Station, a critical medical emergency can trigger an emergency return to Earth within hours. On Mars, that option simply does not exist. Even if a return vehicle happens to be fueled, ready, and sitting on the launch pad, the flight home still takes between 6 and 9 months depending on the transfer window, and the crew member would likely need advanced medical care long before arrival. Because of this brutal reality, current mission planning places enormous emphasis on training every crew member in advanced trauma medicine, autonomous surgical capability using guided robotic tools, and stocking pharmaceutical supplies and diagnostic equipment far beyond what even the International Space Station currently carries. Some proposals include AI-assisted diagnostic and surgical support systems, specifically because there will be no doctor on call and no rescue helicopter, only the training and equipment already on the ground when the emergency happens. The fifth scenario is the failure of in-situ resource utilization systems, commonly called ISRU, which are the systems designed to manufacture rocket propellant, breathable oxygen, and water directly from Martian resources such as atmospheric carbon dioxide and subsurface or polar ice deposits. This technology is absolutely central to any real Mars colony plan, because it is far too expensive and heavy to bring every drop of fuel and water needed for a return trip all the way from Earth. If the ISRU system that produces the methane and oxygen propellant for the return rocket fails, the crew could find themselves with a functioning spacecraft sitting on the launch pad with absolutely no fuel to get home. This is considered one of the single greatest risks in the entire Mars mission concept, and mission planners mitigate it primarily through redundancy again, building duplicate ISRU processing units, pre-landing robotic verification of the system's performance before any crew ever launches, and maintaining a strict rule that no crewed mission departs Earth until the propellant production system on Mars has already demonstrated it can fill the return vehicle's tanks completely. Verified robotically in advance. The sixth scenario involves a catastrophic failure of the ascent vehicle itself, the rocket designed to lift the crew off the Martian surface and into orbit to begin their journey home. If this vehicle suffers structural damage, an engine failure, or any fault that renders it unlaunchable, the crew is stranded on the surface with no way to leave, regardless of how much fuel or supplies they have. This is where the concept of a backup ascent vehicle becomes critical. Serious mission architectures propose landing a second, fully redundant ascent vehicle, either alongside the primary one, or as part of a subsequent robotic cargo mission during the following transfer window, essentially pre-positioning a spare rocket on the surface specifically, so a single vehicle failure can never strand the crew permanently. This is directly inspired by the lifeboat principle used on ships since the Titanic disaster. Always carry more capacity than you think you will ever need. The seventh scenario is a total loss of communication with Earth, whether from equipment failure, a solar event disrupting radio transmissions, or damage to the colony's antenna systems. While a communication blackout alone would not necessarily be lethal, it removes the crew's ability to receive real-time guidance from mission control on Earth during any other emergency, forcing them to rely entirely on pre-trained procedures and onboard decision-making. This scenario has pushed mission planners to design extremely detailed contingency playbooks and train crews to operate with near-total autonomy, since even under normal operating conditions, the communication delay between Earth and Mars ranges from about 4 minutes at closest approach to over 20 minutes at farthest distance, making real-time conversation with mission control essentially impossible, even when communication is working perfectly. The eighth scenario worth examining is a supply shortfall, running critically low on food, water, or spare parts due to a resupply mission failure. Cargo missions to Mars are typically sent ahead of crewed missions during earlier transfer windows specifically to preposition supplies. But a launch failure, a landing failure, or a damaged cargo vehicle could mean an expected shipment never arrives. In this case, the colony's survival depends on the redundancy built into its own food production systems, typically proposed as a combination of pre-stocked dehydrated and shelf-stable rations, alongside greenhouse modules capable of growing crops in Martian soil, supplemented with nutrients. An approach partly inspired by real experiments already conducted aboard the International Space Station, growing lettuce and other crops in microgravity. Mission planners generally require colonies to maintain at least one full additional transfer window's worth of consumables in reserve, essentially an 18 to 26-month buffer, specifically to survive a single failed resupply cycle without ever needing an emergency rescue at all. Now let's talk about the scenario everyone eventually asks about. What if Earth actually needs to launch a genuine emergency rescue mission to Mars? This is where the true engineering nightmare begins. First, any rescue vehicle would need to already exist, fully built, tested, and ideally positioned either on the ground ready for a rapid launch campaign or already in space. Building a Mars-capable spacecraft from scratch after a disaster is announced would take years, far too long to help anyone. This is why modern rescue concepts increasingly focus on reusable heavy lift vehicles like SpaceX's Starship, specifically because having a fleet of reusable ships already flying regular Mars cargo and crew missions dramatically shortens the time needed to prepare an emergency flight, since the hardware and launch infrastructure already exist and do not need to be built from zero. Second, even with a ready vehicle, the mission still has to wait for a viable transfer window unless it is willing to accept an extremely fuel-expensive, slower, and riskier trajectory. Mission designers have studied faster transfer trajectories that could shave a couple of months off the standard journey by burning significantly more propellant, but these come at a steep cost in payload capacity and fuel margins, and they are really only feasible with next-generation propulsion systems, including nuclear thermal propulsion, which has been undergoing renewed research specifically because it could cut Mars transit times dramatically compared to today's chemical rockets. This is one of the major reasons space agencies are investing in nuclear thermal and nuclear electric propulsion research today, not just for colonization efficiency, but specifically to shorten the rescue response time in a genuine emergency. Third, once a rescue ship actually reaches Mars, it still has to survive atmospheric entry, descent, and a precision landing near the stranded crew, all of which are famously difficult even for uncrewed robotic missions. A challenge engineers have nicknamed the 7 Minutes of Terror because of how little control ground controllers on Earth have during the automated entry and landing sequence due to the communication delay. A rescue vehicle would need to land within walking or short rover driving distance of the stranded astronauts. Since Mars has no infrastructure equivalent to roads, airports, or emergency vehicles capable of covering long distances quickly across the planet's rugged terrain. Fourth, and often overlooked, the rescue crew or robotic system aboard the rescue vehicle would need enough consumables, life support capacity, and space to bring the stranded astronauts home safely, which means the rescue mission itself has to be planned with enough surplus capacity from the very beginning, essentially designing every crewed Mars mission with the assumption that it might one day need to double as a lifeboat for another stranded crew. Given all of this, what is the actual, most credible plan that serious mission architects have settled on for handling a genuine colony failure? The consensus that has emerged from studies at NASA, from SpaceX's published Mars architecture concepts, and from independent aerospace engineering research, group centers on prevention through radical redundancy rather than reactive rescue. That means multiple independent habitats instead of a single base, so a catastrophic failure in one does not doom the entire crew. It means multiple ascent vehicles pre-landed before any crew arrives. It means power systems that do not rely on a single source, ideally nuclear reactors, as the primary supply with solar as a supplementary backup. It means life support systems with fully independent backup loops. It means at least one full transfer window's worth of stockpiled consumables at all times. It means extensive crew training in medicine, engineering, and improvisation, far beyond what astronauts on the International Space Station currently receive. And it means building a reusable transportation fleet regularly flying between Earth and Mars, so that the infrastructure for a genuine emergency mission already exists rather than needing to be invented after disaster strikes. There is a phrase used often in mission design circles that captures this philosophy perfectly. The best rescue mission is the one you never have to fly. Every redundant system, every backup habitat, every duplicate ascent vehicle is fundamentally a rescue mission that has already been completed before the crew even leaves Earth. This mirrors the hard lessons learned from Apollo 13, where the crew survived not because of a fast rescue from Earth, which was physically impossible at their distance from home, but because the spacecraft itself had just enough redundant systems and just enough brilliant improvisation from mission control and the crew together to turn the lunar module into an improvised lifeboat for the return journey. Mars planners study that mission obsessively today, not as a story of NASA sending help, but as a story of a crew and a spacecraft solving their own survival with the tools already on board. Because on Mars, that will almost always be the only option available. So when you strip away the science fiction imagery of a heroic rescue ship swooping down through the Martian sky at the last possible moment, the real answer to how humanity would handle a Mars colony failure is far less dramatic and far more disciplined. It is redundancy engineered years in advance. It is duplicate systems nobody ever wants to use. It is stockpiles calculated down to the kilogram. It is crews trained to be their own doctors, their own engineers, and their own rescue team. Because for the first time in the history of human exploration, the rescue team simply cannot get there in time. Mars will be the first place in human history where survival depends entirely on the preparation completed long before anyone ever needed saving. If this deep dive into the real engineering behind a Mars rescue mission fascinated you, make sure you subscribe and turn on notifications, because we are going to keep exploring the hardest problem standing between humanity and becoming a multi-planet species. And trust me, This was only scratching the surface of what it will really take to keep the first Mars colonists alive.